structures, try to reorder them, try to reorder the expected sequence of elements. Some special attacks. Version fields are very particular in many protocols and file formats. They are kind of like a key that opens up the remainder of the protocol, for instance. So a piece of software might blindly believe a version field in what kind of data will maybe come later in the protocol sequence or inside a particular message. So many times a version field is a very easy way to completely undermine the expectations of the software. Another thing is that when some protocol feature is, for instance, removed from a future version of the protocol, is it usually so that the implementations that are then ported to support the new specification are the parts really that pass the old protocol version, do they get removed or protected from usage? So usually what happens is that there's just added features, added ways to pass the new version of the protocol, but all of the old CRUD still remains within the software. All of the constructs that have been used to pass and process the old version of the protocol. And sometimes when a new version is released, testing is not that important anymore for the old version. So most testing concentrates on testing the next version, the newest version of the protocol, and it's really nobody really cares about the old version anymore. So you might find some locations in the code that have not been tested for 10 years maybe. Attacks against the version expectations is to try and claim to use a valid earlier version, but then use a completely different data within the message, or then try to use a completely unspecified version. Who knows what happens when you try to use like IP version 17 or something. Then another special attack case is the use of obsoleted or proprietary extensions. So there might be some specifications that have been forgotten about already. Some old internet drafts, for instance, from IETF that have been discarded, that have been expired and nobody really implements anymore. But there might still be code for handling these kind of obsoleted features. And again, this code might be much less tested or even forgotten about completely. So there might be a module that passes a particular obsoleted protocol specification, and nobody really even cares about testing it. The architecture for handling extensions is usually very general. There is things added over time to many implementations to handle new extensions. So over time it becomes a total mess because there are public extensions, proprietary extensions, obsoleted extensions, and extensions that you should be prepared for but which have not been specified yet. So any kind of code for handling extensions is very fruitful ground for basically doing anything. Even random fuzzing for extension fields is surprisingly effective. Also, if there are proprietary extensions, somebody might have done reverse engineering for these proprietary extensions, let's say competitors' extensions, and hacked together some kind of like a mutant code that takes a look at these proprietary extensions and tries to make sense of them. So if somebody has not had full access to the specifications for these proprietary extensions, it's very likely that the code is it's a half-assed attempt at understanding the proprietary format. So you should always try to look for any obsoleted protocol features or file format features and try to break those things as well. Or try to emulate some version of the protocol that is obsoleted. Now, usually when we look at designing anomalous data, breaking the data from several locations is not typically that fruitful, and it's kind of a surprising thing. You would probably assume that when you fuzz multiple things at the same time, you are able to crash the software more effectively. But usually a single anomaly, a single input is enough to trigger one individual flaw. When you start adding the amount of fuzzed inputs into one single packet or one single file, you might miss some of the underlying problems. You might end up in a race condition, so to speak, where your fuzzing inputs one of the fuzzing inputs triggers a particular flaw, but the other fuzzing inputs would never reach the flaws that would be out there. So I'm getting the red card now, so I'll have to skip a few things, but let's move a little bit forward. You can take a look at the data or the slides later on if there is some things. I want to stress a couple of more things. It's only going to take a minute or two. So when you are creating invalid inputs or malicious inputs, you should always try to be first as correct syntactically as possible. So if there are some checksums, message digests, different kind of signatures, for instance, mandated for a protocol, for instance, you should always make your attacks use these kind of mechanisms completely, and then only then start to undermine the underlying data structures. So try to be as valid as possible, and then start tweaking the minute things that will then create or trigger the vulnerabilities. So if a protocol requires you to calculate a checksum, just do it. Make a model that does the checksum, or the timing things that were discussed in the earlier wireless talk. So you should always try to be as valid as possible, and then start creating attacks. Like I said, everything is TLV, and this is probably the most important thing to understand, is that you should always try to understand the next level substructures that you are trying to break. I have a couple of example attacks here at the end. I'll actually not go into this in that much detail. You can take a look at the links and the examples in more detail from the slides that will be up on the DeepSec website. I have an example of a length attack against a particular Bluetooth implementation. So I was hoping that maybe Marcel could talk about this at some point. Underflow attack. One example from a SIP implementation, and a naive way to protect against this attack. Implicit value from X509. This is the famous parasitic keys attack, where simply choosing particular values for public keys, for the public exponent and public modulus values, caused degradation of service in many implementations. Again, things with implicit values combined with usage of obsoleted protocol feature. Repetition, again, combined with an implicit value expectation. These kind of things. State machine mangling. So this particular attack looked at sending a very advanced broken sequence of SIP requests, and then caused a problem in a particular SIP implementation. So I'd like to, in the end, I'd like to thank my colleagues from Codenomicon for some of their research around this area. And then we don't have any time for questions, but I'm sure we can have one question if somebody really feels the need to ask. Or you can come and discuss with me later on, or in the cocktail event in the evening. Any questions? Okay, go ahead. Yeah, so my company, we make fuzzers for various protocols and file formats. We have a fuzzing framework that we use to create the fuzz tests. But this is not a product pitch, so go to the website if you want more on that. But yeah, we have a fuzzing framework for doing this, as do many others nowadays. Okay, thank you.